Okay, so it's a pleasure to have everyone in. So we continue with virtual seminars in Precambrian geology. And so I start putting schedule for next year after probably this week. And so I will be contacting people, and if people have suggestions, send it to me or to Alex. So for today, it's a pleasure to introduce Kurt Konhauser from University of Alberta. Kurt did his PhD at University of Western Ontario, working on sort of recent geochemistry and silicification in Amazon River. But shortly after graduation in 1994, he took position in University of Leeds. And in, I guess in 8 years after it, he left and joined University of Alberta, where he stayed for the rest of time. So Kurt has sort of ability to see the gap in knowledge and kind of narrow down and go full speed on it. And so one of his early achievement was that he realized that interface between solid earth and microbiology is sort of not populated. So he wrote a book on geobiology, which is now one of the highly cited books. He worked on ion formation and interface between microbes, environments, and absorption of metals on microbes. In addition to his research activities, he sort of had a community impact by being a head editor of Geobiology Journal. And he also organized 2 conferences on geobiology in Banff, Alberta, and organizing a 3rd one in May. So with this, it's a pleasure to have Kurt, and I pass it to you.
All right. Well, thank you, Andre, and thank you for everyone for making the time. So I'm going to talk about a theme I've talked about a lot in the past, and I keep coming back to, probably because of, although I work on a lot of things, it's probably my favorite thing to work on. And given the number of Science and Nature papers in the last 5 years, it seems like quite a few of you are interested in this as well. So let's start with a slide that's an update of Tim's 2014 one. Just basically came out. And I'll just walk through really quickly some of the major features. Now, the take-home message, really, I think, from the work on early O2 is that it's much more dynamic than we ever thought. So, you can look at the broad major steps, like low oxygen jumps up after GOE to higher oxygen, and then it jumps up basically after NEOE, and once again in the cellular with plants. We've known that for a long time. If you looked at Tim's 2014 model, you'd also see that there's a lot of these arrows suggesting there's fluctuations. So that is actually the case. And it's becoming more so the case that the longer we go on with this, the more we're realizing that actually Hiroshi Yamamoto was right a long time ago in that the atmosphere is kind of an oxygen yo-yo. So I just want to focus on a few things. The one here is that this thing that we used to call the Great Oxidation Event, 2.4, used to think it went to about 2.3. That's based a large part on Andre's Nature paper, where he basically at the 3rd glaciation in Huronian showed that you started getting sulfur MIF patterns. That's these patterns right over here. But what a recent paper from Simon Polton, which I'll talk about in a minute, in 2021 has shown is that, in fact, there is a lot more going on at this point in time than we thought. And indeed, the oxygen seems to fluctuate quite a bit, all the way to 2.2. Why that's important is because there's no longer a clear break between what we thought was the Great Oxidation Event and what we now think is the Loma-Gundi event. And I just put up a term that Andre and Dick Holm coined, the oxygen overshoot, where oxygen appears to go up possibly to near modern levels and then drop again. And you can see through here, we have lots of upward and downward arrows. These are all pieces of evidence from, the geochemical record suggesting that oxygen has gone up and down. But I think the narrative today, when we're talking about O2, is not talking about any particular time, but it's talking about steady states and how we have a steady state that's, very low oxygen, less than 10 to the -5, 10 to the -7, depending on which paper you talk about. Another steady state around 10 to the -3, and then there's one above 10 to the -1. So really viewing the Earth as being in a steady state and that periods of time not being in this steady state. For example, there's Great Oxidation Event where it looks like oxygen is jumping around. Now, the question is, with the Loma-Gundy, for example, do we just go into the next steady state, which is 10 to the -3, or do we actually go into even a higher steady state where we go near modern? And that's the question. It all depends on whether or not you believe in what the Loma-Gundy is. But I just want to focus on this part right now, this part which says whiffs and benthic mats. So back in 2007, I think it was, Errol Anbar wrote that famous paper, The Whiff of Oxygen, that suggested that there was a temporary increase in O2 in the atmosphere that lasted for a while, and then it went back to low before the actual GOE started. Now, there's a lot of papers in the interim that have shown periods of oxidation, or at least oxygen presence, between, say, 3.2 billion years ago and 2.5. And I'm just trying to click on here, sorry. I would refer anybody who really wants a good update on that to look at Chad's paper here, because he does cover all the details. But I think it's very hard now for anyone in the community to argue that cyanobacteria evolved right before the GOE, given the fact that there is so much evidence, whether it be molybdenum, rhenium values, whether it be cerium anomalies, whether it be nitrogen isotopes, chromium isotopes, there's molybdenum isotopes. There's a large amount of geochemical evidence suggesting there was some oxygen around. Now, to me, the question is where is that oxygen? Is it atmospheric, or is it associated with what I call these benthic mats? So Ariel and people still today will view these as whiffs, where we have basically this temporary pulse of O2 coming from an oxygen oasis, perhaps in the ocean, perhaps on land, basically feeding O2 to a specific spot where for a period of time we get oxidation. So I think going back to Ariel's paper, it was based on a large molybdenum peak that was something like over 2 meters. So what's that? Something like 2 million years of deposition time. So you've got a model that's trying to invoke that there's temporary oxygen for a long period of time. Now, where that is a bit problematic, at least to me, and it's not that it's wrong, it's just I just don't get it, is with oxygen, with the mixing time in oxygen in the atmosphere being pretty quick, less than 5,000 years. And with Kevin Zonley having shown that at very low concentration, basically oxygen doesn't mix. It's just hard to imagine the oxygen being in situ in one place for such a long time if it's being not deposited atmospherically. So where Stefan Lalonde and I in 2015 came in is we argued that instead it was something like a benthic mat. So you can imagine a cyanobacterial mat growing on the surface of a rock, producing O2. That O2 can diffuse a bit up, but it also diffuses down. It oxidizes the minerals underneath, let's say pyrite, or could be molybdenite, putting things like sulfate and molybdenum into solution, which could carry to the ocean and thus indicate oxidative weathering, but it's independent of the actual atmosphere. And in terms of looking at life on land, I think this is something that's gaining much more momentum. So I just flagged this paper that Noah and a few of us did a few years back, talking about life on land and that being a place where basically lots of oxygen could have got a kickstart. So I'm going to give my story away. Why is there a gap in time between cyanobacteria evolving O2 and the GOE? I think it's just habitable space. So this is what this paper kind of talks about. So, sorry, I missed this one. So I wanted to flag this paper from Alicia because a lot of the work done on looking at the topography of O2 through time has always looked at the maximum value. And it hasn't really concentrated on what the lower value was. So just how low was O2 back earlier on in the Archean? And what this study basically did is it used new weathering rates for sulfides, along with some modeling, and it re-examined the molybdenum and molybdenum isotope data in shales back in time. And what they suggested is that at low oxygen levels, at 10 to the -7, you could still get some oxidative weathering of the molybdenum from land into the oceans. This is important because over here we have our sulfur myth at 10 to negative 6. Now, I know Kevin Zonley argues for being the 10 to negative 7, but neither here nor there. We can envision an environment where we have a sulfur myth signature suggesting that the atmosphere is functionally anoxic. Yet on land, we can still get oxidative weathering of a small amount of the sulfide phases. And that also explains why we don't really lose these detrital pyrite grains until something like 2.4, whatever it is like that, because the oxygen that's been produced is not enough to completely oxidize all the pyrite. In other words, there's more pyrite than there's oxygen. So pyrite stays around until at some point in time when there's enough oxygen, we've reached a steady state, let's say 10 to negative 3, and we begin to oxidize all of it. We get paleosols and all the other features. So we're looking at least going back into the Paleoarchean, lower levels of something like 10 to negative 7. Now, how low does it ultimately go? Well, it's hard to say. I mean, I was looking through some literature, and Jim Casting's old work suggests something like 10 to negative 11 if you're looking at photolysis of water. So, but the point of what I like about this paper is that we've actually trying to put numbers on the lower limit in addition to the upper limit. And then I just want to refer to, this is a figure that Andre's been using for a while, but it's been updated in Simon's 2021 paper. Now, the story used to be that the last bit of sulfur myth we get ends around the glaciation, third glaciation right here. And after that, we get permanent oxygenation. And then we move into Lomagundi. So the question always was there a gap here? And that's what we thought there was. What Simon's new work is what he suggested is that there's actually sulfur myth signals still before the fourth glaciation to the time ball in South Africa and after. In other words, oxygen is flip-flopping from 10 to negative 7 to some value above 10 to negative 7 so that we get a sulfur myth. So this is our unstable phase, our oxygenation, where things can go up and down. And, you know, Kevin, the Wogan paper that I referred to earlier on from Kevin Zonley and Catling, what's cool about that paper is they talk about, you know, how long does it take to go from a low O2 state to a higher O2 state? And their argument is that it could take hundreds to tens of thousands of years. So it can be pretty quick. You've just got to scrub out all the reduced gases in the meantime. Similarly, you can drop from a higher oxidation state to a lower oxidation state reasonably quickly. But this is our unstable phase where anything can basically perturb it. So it could be a glaciation, like in this case. It could be a large igneous province. It could be high rates of chemical weathering leading to a nutrient bloom. Anyway, something at this period of time can cause it to go up and down quite steadily until we get to this point here. Now, this point here is where we have Andre's oxygen overshoot, where he would argue that oxygen goes up to very high levels. And it runs at the same time as the Lomagundi event. Now, what the Lomagundi event essentially is, it's this perturbation in the carbon isotope record in carbonates that runs for something like 160 million years, from about 2.2 to 2.06. So it all depends on who you talk to. Now, there is debate about what this actually means. The traditional view is that the reason we get this positive isotope fractionation is that we've buried a lot of organic carbon at that time. We bury a lot of carbon-12, leaves carbon-13 in the water column, which then gets incorporated into the limestones and dolomites. And whatever it is, we see that there's other examples right beforehand of small peaks, but nothing in the rock record mimics the length of this. Now, others have argued that it has nothing to do with organic carbon burial. It could be something about, you know, you've got volcanic emissions that have got more carbon-13 rich gases. Others have argued that it could be fermentation. But I make the point that even if you argue that this represents fermentation, it still represents high biomass burial because to get to fermentation, you've got to burn through all your other electron acceptors. Now, a recent paper from Dawn Sumner in AEM came out, and she basically argued that this is a methane signature. But what's really kind of cool about that paper, she argued that the reason we drop out of this is that's when we start evolving basically respiration, other heterotrophic respirations that basically preclude the methanogens from surviving. So that's a tipping point for her in terms of the biology. I think Andre would still argue that what this is more likely reflection of is that we're no longer weathering the crust. The original crust that had high pyrite led to a lot of acidity, caused lots of nutrients to come into the basins, and instead it's recycled material that started off in the Lomagundi as sediment. But either way, the question really is, to me, is if you believe that this is real, oxygen peaks up to a higher state and then it drops again. And I just want to once again cite a couple papers. This is Simon's recent paper and a very recent paper from Chad looking at the fact that we get these fluctuations as well in the water column. In this case, they use molybdenum and thallium. So the consensus seems to be that during this period of time, the so-called GOE, that we have oxygen going up and down. And in Simon's paper, he's relabeled this the Great Oxidation Episode. So whatever you want to call it, something significant is happening at this point in time. But certainly the traditional GOE seems to be running from 2.45 to 2.22. So that's the background. Where do I come in with some of this work? So as Andre mentioned, I work a lot on banded ion formations. I'm not going to go into great detail about that, but the main thing is really there's two ways of looking at the ion formations. One, most of them are chemical precipitates, the classic banded ion formations. This is stuff that precipitates out of seawater like a salt. And so it's higher in iron and silica, suggesting the oceans were ferruginous and siliceous. And then we have things called granular iron formations. These are basically reworked iron formations. These are near shore, high clastics content. And this is just a typical picture of a banded iron formation. And really shortly, I have made the argument for a long time now that banded iron formations are biological. In other words, you had an ancient ocean that was ferruginous, but you have to convert that ferrous iron ultimately to ferric iron, at least in my model. Okay, I'm going to talk about this for a second. Most of us believe banded iron formation started off as something like ferrihydrite. To get to the ferric iron, you need an oxidant. The oxidants, you can have UV, which I don't have up here, UVA, UVC. And that was work from Braderman and Karen Smith in the 70s where we talked about that. But basically, there's three biological ways. There's cyanobacteria. They produce O2. That O2 inorganically reacts with the iron, forming ferrihydrite. At some point in time, when O2 levels increase enough, you actually get these things called cumulative autotrophs, things like Gallionella, Leptothrix. These are bacteria that make a living out of oxidizing the ferrous iron using the O2. And then underlying it, you have these things called phototrophs. These are anoxygenic photosynthesizers that also basically metabolize using ferrous iron as their electron donor. So this is work that really Clara Chan and Dave Emerson have championed, and this is work that Andreas Kapler in Tübingen has really championed. And in any of these models, what you basically have is you have a composite of biomass and iron oxides settling to the sea floor. There they undergo diagenetic alteration, producing things like siderite, magnetite, and greenolite. Now, I will say there is a community, and you're all probably familiar, a community that would argue that banded ion formation started off as a ferrous silicate instead. Now, I don't want to really get into a major discussion about why I think that's not correct, because we're dealing with people who are really quite bright. They've made some very good points about finding what they think are primary green light in iron formations. But nonetheless, I think there's a fundamental flaw. But before I get to that, I just want to make a point. Does anyone know actually where that original idea, and I think it's the original idea that Birger talks about in one of his papers of the green light? It's from him. So back in 2007, I wrote an EPSL paper trying to discount photooxidation, UVA, UVC. And what I said is that in shallow water, you do indeed have UVC, UVA photooxidizing ferrous iron. But in the presence of biology, the bacteria do it way faster. So it's not an issue of whether or not you can get inorganic photooxidation. You do. It's just that the biology is a lot faster. But what I also suggested is that imagine the open ocean where the ferrous iron is coming out from a deep sea vent. As it's making its way onto the shelf where the BIF are forming, and this is all anoxic water, there's no reason to believe that you don't get things like green light or siderite precipitation. But here's where I will argue with the people who think this is the primary of BIF, is that the BIF are forming on the continental shelf where you've got biology. Ultimately, to make the argument that green light's a primary precipitate, you have to argue against biology being there. Now,
is that okay? Please.
why that is a real
Awesome,
problem
dude. Thank you.
is that if you're talking about iron formations forming around the GOE, like the Dales Gorge, we know that the reason we have the GOE is because we have shallow O2 production from cyanobacteria. So by default, we've got cyanobacterial activity in the water column. So how we now discount it so that these can be primary precipitates is something that I would really like someone from that camp to actually explain. And on top of that, we've done other things like we've basically modeled how long would it take oxygenated fluids to move through a BIF, and it takes way too long. We've recently published a paper in GSA Bulletin looking at the weathering rinds on the BIF. And what we essentially show is that even a BIF that's been sitting out in basically open to the atmosphere for a long time, the weathering rind is like basically microns thick. And basically, if you select your BIF properly, you can get primary BIF from outcrop. You don't need to have core. In other words, there's lots of reasons why I believe that the iron start off is ferric. And the reason I think this is important is because a lot of the work that I do and others have done as well is looked at the iron formation record as a proxy for ancient seawater chemistry. And I'm going to use this slide to lead into one of my papers. But the reason I'm really with chromium is there's a lot of papers that talk about different proxies for timing the GOE. Sulphur myth probably being the smoking gun. But I think the chromium record is really good too. Now, for all due credit, this was not my idea, the chromium. This is actually Robert Fry's idea. And he talked about chromium isotopic fractionation band 9 formations. And essentially, wherever you see a positive isotopic fractionation, he suggested that that represents oxygenation. And the model, so I keep getting my face in the middle of my screen here. The model essentially goes like this. If you oxidize chromium 3, let's say from chromite to chromium 6, which is soluble chromate, and that's what apparently is getting into the ocean, you don't do it directly through O2. Instead, what happens is O2 oxidizes manganese 2 to form manganese 4. Manganese 4 is in your oxidant for chromium 3, converting it to chromium 6, i.e. soluble chromate. This gives you an isotopic fractionation, a positive one, which if you take a look at the BIF, that's what this is basically representing, this process here. Now, this gives you a fractionation. Now, that chromium 6 enters the ocean and gets very quickly re-reduced by all the ferrous iron in the ocean, which we know is there because we have the BIF. That converts ultimately to a chromium iron hydroxide, which, because it's quantitative, even though it has an isotopic fractionation, doesn't really get recorded. But the take-home message is that the isotopic fraction in this represents this step, which represents ultimately O2. Now, what basically Fry and them argue is that already at 2.8, because you have this fractionation, that there must have been O2. What I contended with them, or I contested with them, is the fact that the iron formations they used here are what we call these algoma type. These are ones that are formed at submarine volcanic systems. They're not the ones that when we talk about superior iron formations that form on the shelf, which would reflect continental weathering. But where I do give them a lot of credit is they're the first ones actually to point out that O2 may have dropped and then picked up again here at the Gunflint. So they were way ahead of the time in terms of talking about the O2 fluctuation. I just disagree a bit about what the chromium numbers mean. So to get to our following paper, what we did is we don't do isotopes in my lab, but we do bulk concentrations. So we looked at chromium and iron formations through time. The red are basically band 9 formations, like superior type. The blacks are algoma, and the blue are what we call basically granular iron formations. Now, what we find is that chromium begins to ramp up about 2.48. By 2.45, it's pretty high, and then it peaks at 2.32 with the time ball, with the oolitic ironstones there. Now, we'll also point out that for these ones over here, in terms of the Pangan and Kurman, the high concentrations come from the layers which are basically have lots of tritous material in it, and same with the Cowie in Brazil and the Wheelie Wally in Australia. In other words, it's what I call the dirty BIF, the BIF that have a high classic component that show the chromium signature. Now, why that's interesting is normally when I do work on BIF, I like to look at those which have been filtered, where we basically take out anything with 1% aluminum in it. In other words, we want to get the chemical precipitates to talk about bulk seawater. We don't want the dirty stuff that's got contamination from land. But when you do that with the iron formations here, we find no chromium in it. And that's not surprising because remember, if Fry is right and it's chromate coming into the ocean, chromate instantly gets reduced by ferrous iron. It's never going to accumulate in seawater. It's going to precipitate near shore. And that's exactly what we say. But here's to me kind of the coolest point of all of this is this peak at 2.32. It's a peak we never see again. Now, if I was to attribute this simply to O2 in the atmosphere, I could make the reasonable argument that I should see high chromate even in these modern, modern iron exolites and in volcanic deposits, but I don't. It seems like it's a one-off here. So what happened here that never happened again? So that led me to think about, well, what's another potential way of mobilizing chromium? And if you take a look at a speciation plot, chromium can be either soluble in terms of the +3, or it can be in a +6. To mobilize chromium-3 from chromite, though, and to keep it in the reduced state, you need to have acidic conditions. So a great example of where you would get acidity is, think about today an environment like an acid mine drainage site, where you get pyrite oxidation, low pH conditions, and that could solubilize the chromium. Now, what we suggested in our paper is that the chromium that we see in the iron formation is not from chromium-6, but it's from chromium-3 instead, due to acidification. And that acidification comes about from pyrite oxidation. So what we imagine is, think about this. You've got a land surface. Actually, I should do this one here. A land barren surface, right? There's no plants. It's you've had pyrite built up in the outer crust for a long time, and now we've got O2. That O2 causes pyrite oxidation, which causes a decrease in pH, creates acidity. So we begin to solubilize lots of stuff, things such as chromium. So you can imagine that your chromium gets mobilized either as soluble chromium, or it could be associated with a clay phase, but it's being mobilized from land to the ocean where it precipitates out quickly. Further out, you don't get any chromium because the chromium-3 would never make it out, because the same as why chromate does, because it gets reduced by iron, the chromium-3 can't extend because instantly chromium-3 hits, let's say pH 4 rivers, hit suddenly pH 8 oceans, precipitates out. So that's our model for how chromium is mobilized. It's a one-off because the outer crust had lots of pyrite, had never seen O2 in large amounts before. Now it does. That pyrite oxidizes, creates acidity, which dissolves things like the chromite. But then this leads us to some other thoughts. Well, if you can dissolve chromite, how about things like phosphorus from apatite? Now, if that's the case, if you transport a lot of phosphorus from land, you're obviously going to trigger things like high primary productivity in the coastal settings. That could lead to a large amount of organic carbon being buried, and voila, you get your Lomagundi event. That's 2.2, 2.06. Now, I just want to point out one thing. As I said, there is not universal consensus that the Lomagundi event, now the isotopes are real, but whether they represent intense carbon burial is something that's debated. Others have argued whether it's local signatures versus global signatures. But you have to look at the fact that you've got 160 million years, even of these local signatures, suggesting probably high organic carbon burial to give you this. Now, one of the arguments has always been is, well, where is the organic carbon? Because if you look, for example, in the Onega Basin in Russia, you find that you don't get these organic rich layers until above rocks that are younger than the Lomagundi. But I happened to come across this paper a couple years back from Parnell, and I kind of thought this was really cool, even though I know nothing about orogenes. But what they suggested is that between 2.1 and 1.9, there's a lot of mountain building taking place. This was after Kenora land has basically been rifted apart, and now everything's colliding together again. And what was interesting in this paper is that they looked at the organic carbon content of a lot of these orogens and found that a lot of the shells are essentially black shells with high organic carbon content. So they've even made the argument that all this organic carbon helped with the orogenes, and that this is where our organic carbon from the Lomagundi has ended up, in the mountains. Now, whether it's true or not, I don't know, but I did think this is kind of a cool way of looking at it, because it does solve, to me at least, the issue of where's the carbon. So Andre and Dick write this overshoot paper in 2012 where they really lay out a lot of the steps about how it all forms. So I really recommend anyone reading that if they haven't. But one of the questions that wasn't answered in that paper, or is it in mine that was the year before, was how does the phosphate get to the oceans? Now, it's usually assumed it's going to be in solution. But if you take a look at phosphate mobility, you find that most of the phosphates actually transported in suspension, whether it's with organics, whether it's with iron aluminum oxides, or whether it's with clays. Now, going back to 2.3, we don't have, well, potentially, we don't have a lot of organics on land. Now, we could have microbial mats, but we certainly don't have vegetation plants and stuff like in that context. Iron aluminum oxides. Now, are there going to be a lot of iron oxides at that time? No, because we've argued for low pH conditions to solubilize everything, which means that ferric iron is also going to be solubilized. but it certainly does mean you can get aluminum oxides. And in fact, if you look at paleosols from that time, they have a high aluminum content. And then there's certainly clays, like kaolinite. So in this paper, written by my former PhD student, who's now a prof at Northwest University in China, we argued that the phosphate was actually mobilized by clays, what we call this kaolinite shuttle. And really quite briefly, when you take a look at the work that Weidu did, we looked at desorption of phosphate to clay. This is basically just isotherm looking at different concentrations of phosphate to see how much could be bound. And we looked at p-adsorbed on freshwater conditions. So this is freshwater ionic strength at pH 4, 6, and 8. And then we did one at marine ionic strength at pH 8. First thing you note is that at pH 8, you don't bind much phosphate. It doesn't matter what the ionic strength is, you simply don't bind a lot. You bind the most at low pH. Now, and this inherently makes a lot of sense because at low pH, basically the surface of kaolinite is going to be protonated. Phosphate basically deprotonates. The first deprotonation happens around about 2.7. So you've got H2PO4 2 minus basically binding onto positively charged AlOH sites on the kaolinite. So it makes a lot of sense that at low pH, you're going to bind a lot of the phosphate on the kaolinite. Then what we did is we did what we call these dynamic experiments where we loaded up the clays with phosphate. And then into that solution, we basically upped the ionic strength and upped the pH to try and mimic seawater. And what we find is with the kaolinite, what happens is you get a progressive release of the phosphate. Why? Because the pH is increased, which means the kaolinite surface is no longer positive, but it becomes neutral to negative. Phosphate at pH 8 is definitely negative. So these two things are not going to bind strongly together. The reason I show this part right here, the green is hematite. No, sorry, the blue is hematite, the green is gibbsite. We see no such trend. Why that's important? You can argue that you can get phosphate mobility from land to the oceans, let's say associated with an iron oxide or aluminum oxide. But the point of the matter is, as soon as it hits seawater, it's not re-releasing its phosphate. And in fact, that phosphate gets buried into the sediment column. And the only way it gets remobilized is if you get things such as iron reduction. What we show here, though, is kaolinite will, as soon as it hits seawater, will actually give off some of its phosphate simply because of the pH change. And then another one of my PhD students, Yuhao Li, came up with this really creative idea of let's grow the cyanobacteria. So we took Cyanobacteria syncoccus and we grew them in an experiment where we added, I think it was 5 micromolar phosphate. And we let them grow for 15 days. And what we find is that they're growing, this is that exponential phase, stationary phase, they're growing happy as Larry, and then suddenly they're no longer happy. They croak. The reason they die is because they've run out of phosphate, because all the dead cells have sunk to the bottom, taking the phosphate with them. What we did at one point during stationary phase, though, is we also added to these cells. We added 2 different concentrations. In one experiment, we added 1 gram per liter of kaolinite, the other 2 grams per liter of kaolinite. And in both those cases, we preloaded them up with phosphate at low pH. So now they're sitting in this solution of high pH, knowing that phosphate's going to desorb. And what do we see? But in fact, we see that both populations of cells rebound. In other words, the phosphate which comes off the clay, which desorbs naturally from the clay, which was loaded at pH 4 and now put into pH 8, was sufficient to actually allow these populations of cyanobacteria to survive. So kind of a proof of concept of our idea. So it then leads to the question, can a river sediment plume ultimately lead to higher primary productivity? And the answer is yes. But the question I then ask is this, is that if, as it says, if high atmospheric O2, I'll just keep trying to get rid of the, okay. If high atmospheric O2 results in high primary productivity, then what does the low O2 older than 2.5 tell us? And we're stuck with the 2 standard options. One, there's simply too many reductants for basically that no matter what the cyanobacteria produce in terms of O2, it gets scrubbed out. Or there's something about the environmental conditions that means that the cyanobacteria are not as happy as they could be. So really briefly, evidence for O2, there's, like I said, seems to be a lot of geochemical evidence. I'm a little more dubious about the physical evidence because, you're looking at things like stromatolites, or in this case, mass independent, no, microbial-induced sedimentary structures, or stromatolites, which in this case is the work from Martin Homan looking at the 3.2 Moody's group, suggesting that these laminations are very equivalent to these type of modern microbial mats. But you can't actually identify them and say these were cyanobacteria or not. We just know that we had some kind of mat system in place. Geochemistry, as a geochemist, I'm kind of more amenable to, and this is just one of the many examples. This is work that NOAA did on these about 3 billion-year-old rocks in Pongola, where we looked at the iron formations and we found all this molybdenum isotopic fractionation. In fact, we find a lot of molybdenum-95 being bound in the BIF. And when you look over on this side, the best way to explain the fractionation that we see all the way down to -1 is if you have something like a manganese oxide basically scrubbing out to 95, leaving the 98 in solution, such that seawater then becomes positive. And you can also see that the lowest negative values here are also those with the highest manganese content. So it's not an iron oxide that's driving a signature, it's likely manganese. So whether you believe in that particular model or not, the fact is I think most people will argue that cyanobacteria existed before the DOE. And certainly if you look at the molecular clockwork, they suggest it could be already as early as 3.5. So let's just stick with, okay, what causes the delay? Well, let's say it's reductants, methane, reduced gas, the frigidous oceans, volcanic gases. A lot of you have seen this figure before, so I'm not going to belabor the point, but this is the work I did on the nickel and iron formation through time, where we essentially show that in the Archean we have high nickel and then it drops. Now, in this case, we used abandoned iron formations where we did the filters, i.e. no aluminum, because what we wanted is we wanted background seawater nickel concentrations. And what we essentially show is that we have high nickel in the oceans up to about 2.7. It drops at 2.5 and it stays low. What we said is the argument for that was that this represented a fundamental change in terms of mantle dynamics. The mantle cools, which means you get eruption of less ultramafic rock like komatiites, which are enriched in things like nickel. So if we no longer erupt komatiites, we have less nickel dissolving into the ocean. That gets captured in by the BIF seawater. Now, at that time, I just took for word. So I worked with Nick Arndt and Ewan Nisbet, who said, "Don't worry about it. We know we're on. There was less komatiites at that time, so I just took the word for it." Since then, I've actually hooked up with a colleague, He Liu, who has looked at something I think it's like 96,000 different continental volcanic rocks, looking at the concentration of different metals, in this case, looking at the nickel. And what you clearly see is that you have a lot more komatiites in the Archean, which we said, and also the nickel content is much higher in the Archean. And this is just looking at all the different kinds of volcanic rocks, including things like basalts, dacites, and stuff like that. But the point of the matter being is that clearly nickel concentration in volcanic rocks drops, and that's what we're seeing in the BIF record. But the question really is, it's like, yeah, so what? You see a loss of nickel in the BIF record, but what's the biological story? Well, the story that we came up with is that, nickel is a necessary metal for a lot of cofactors, but specifically so for methanogens. So these are the methane producing bacteria. And what we argued is that if you had a drop in nickel, what that ultimately would mean is that methanogens begin to starve. Now, if methanogens begin to starve, what does that mean for DOE? Well, the argument we made was that before the DOE, you had high methane in the atmosphere. Now, to get eventually oxygen in the atmosphere, you got to get rid of the methane first. And our argument was, well, the methane simply dropped because the methanogens starved. As the methanogens starve, they produce less methane, and then you get a tipping point where you get O2 entering into the atmosphere. Then, like everything, it's always, well, yeah, what's the proof? And I often come back to this particular paper from Eigenbrod and Freeman. And what they've basically looked at is they've looked at the carbon isotope record of organic carbon in sediments, in this case in Western Australia, over 100 million years point of time. And what you see down here, the circles are shallow carbonates, the triangles are deep water shales. What you see is that in terms of the isotopic fraction, in terms of carbon isotopes, they're isotopically depleted. So in other words, they're depleted in carbon-13, which means they're enriched in carbon-12. Now, up here, on the other hand, you see them more within the -30 range. That is kind of typical for cyanobacteria, for autotrophy. And other things like anoxygenic phototrophs basically fractionate even less. So this is what we'd expect today. To get such high fractionations, the argument was that must involve methane cycling. In other words, methane producing bacteria produce methane, other bacteria like the methanotrophs then incorporate into their biomass. Now, what's kind of cool about that is not only does it suggest evidence for O2 back here because you had methanotrophs, but if you go look back here at 2.7, deep water and shallow water all had a methane signature. But by the time you get up to 2.6, it looks like the shallow water has got a cyanobacterial signature, whereas the deep water still has a methane signature. So are we seeing an expansion of cyanobacteria at that time? Well, we know that we've got larger continental landmass, emergent continental landmass at that time. We've got shallow shelves. We actually see that when we look at the stromatolite record, that we see a big jump as you go from the Neoarchean into the Paleoproterozoic. So are we seeing evidence of cyanobacteria now basically expanding their domain because methanogens are no longer competing with them? They're kicking off producing O2 while at the same time the methanogens are starving. So that was the premise to that. Now, one problem that I have, and a lot of other people have, talking about it being basically too many reductants, is that when you model this, we find that it doesn't take a lot of time for O2 basically through cyanobacterial production to scrub everything out. I mean, this is something that Ken Toe talked about back in the 90s, but this is a really good paper from Lewis Ward that looked at everything like the ferrous, iron, the hydrogen, the sulfide, the methane, and at modern rates of O2 production by cyanobacteria, they argue that it would take about 60,000 years to scrub it all the way O2. I've got a PhD student who's working on something similar where we envision a single smaller continent, let's say only 1/10 of the landmass of today, where the 0 to 10 meters depth is all colonized by cyanobacteria. And again, we see very rapid rates of O2 production. And indeed, when I talked about that benthic mat story early on in the very first slide, I was referring to this paper from Stefan and myself in PNAS at 2015. And this is where we argue that perhaps cyanobacterial mats on land produced O2, some diffused up, some diffused down. Imagine my hand is actually basically a pyrite grain that you could actually oxidize that. Now, modern studies have shown these are things called, so this is like an idealized microbial mat that you'll find somewhere. But these are things called soil crusts. We find them in lots of environments today. And I think the models show that, we'd have 25% of the landmass would be covered in things like soil crust today if there wasn't any anthropogenic activity. These things are held together by cyanobacteria and all the EPS they produce. So if you take a look at the O2 production rates and things like this or things like that, what we did is we extrapolated for the entire coverage of the continents. So we took modern continental coverage all the way up to 100%, said, look, if 100% of the land mass was covered with microbial mats producing O2 at modern rates, what would that mean in terms not only of carbon production? It'd be very high. But if you took a look at the O2, what we suggest, so this number here, this line right here, is the balance of O2 production and consumption today. The amount that's basically being produced by carbon burial and the amount that's being used up through weathering and volcanism. If you see where the blue line intersects that, what we're basically looking at is less than 0.1. What's my number here? Sorry. I've got all these things in my way here. It's less than 0.3%. In other words, what our model has essentially showed is that if only 0.3 of all of Earth's surface was covered by microbial mats, oxidized or producing O2 at modern rates, we could basically produce the O2 that we see today that balances it. And then what we did is we took another step because Eva Stoikin wrote a year later a paper looking at sulfur fluxes and suggested that sulfur fluxes that she calculated going back in time must indicate aerobic respiration on land. So if we take a look at the numbers from Eva's paper about how much O2 was required to produce all the sulfate between 2.8 and 2.5, and we see where it intersects with our blue line, once again, we're talking about very low continental coverage. So I seem to have a problem here, right? Because on one hand, I'm arguing that we might have had an expansion of mats on land producing O2. But if that's the case, we should have had to basically the GOE should have happened soon after cyanobacteria evolved. And I don't buy into the argument cyanobacteria evolved at 2.4 because the evidence doesn't suggest that. So again, why does it take longer than it should? Well, I think the really simple answer is that microbial mats weren't as prolific as we think they were. Today, they're much more spotty in their distribution. So I think where we're really going wrong is trying to make the assumption that we have this uniform microbial mat fringing the continents all the way along, producing O2 at modern rates. If they simply didn't produce O2 at modern rates and they weren't as widely distributed as they are today, then clearly they wouldn't have produced all the O2. And then this gets me to the whole point about basically colonizable land. If you've got smaller continents in the past, you've got less colonizable space for the cyanobacteria, you're going to get less O2 production. So this all kind of makes sense. But the one point I want to say, the elephant in the room is aerobic respiration. Because today when you produce, let's say your cyanobacteria produces O2 and carbohydrate, aerobic respirers use that O2 to oxidize the carbohydrate. There's no accumulation of O2 or carbon, right? What if, like in this paper, they suggest that aerobic respiration evolved already about 3 billion years ago? What that means to me is that as soon as cyanobacteria produce O2, their buddies, the aerobic respirers, are now using up that O2. This to me is the one big constraint. This is the one to me, this open constraint of when exactly aerobic respiration actually started. So I think this is one easy way of keeping O2 in check. Now, if we talk about other things, for example, growth limitations, the one that most people tend to lean towards is phosphate. And it'd be rude not to talk about the classic paper on this from Bergman and Canfield. In fact, this is the paper that got me into looking at band ion formations as proxies. And what this paper essentially looked at is it looked at the phosphorus iron ratios in these hydrothermal plumes compared to the phosphorus concentration in seawater. And then, so here's what all the plots are. Then you draw this partition coefficient down to 0. So this is how much phosphate can bind to an iron oxide. Then if you plot the phosphorus to iron ratios of band ion formations through time, that's the orange bar here, where this bar overlaps the red line at the beginning and at the end, that is the equilibrium concentration of phosphate that would have been in seawater to give us the amount of phosphate in these iron formations. Why that's really kind of cool paper is because what it suggests is that the phosphate concentrations, here's my value down here, is an order of magnitude lower than it is today. Now, why this paper was so good, at least in my mind, is because it was an ideal way of explaining why there's a gap. In other words, at a time when there's band ion formation and lots of ions precipitating out of seawater, it's scrubbing out the phosphate. As it scrubs out the phosphate, the cyanobacteria starve. They can't produce at high value. They can't produce a lot of O2. So that was the argument they made. But when you take a look at an ion formation, one of the first things you notice is there's a lot of this white stuff there, and that's silica. So the oceans, before we have things like radiolarians and diatoms, had a lot more silica. And in fact, band ion formations are made of more silica than there are iron. So the question we asked is, what impact does silica have on phosphate sorption? Because being a geochemist, thinking about something like an iron oxide particle, we know these things are like sponges. They just suck up lots of different stuff. So the question is, if you've got phosphate here and you've got silica here, which one wants the iron more? And what we essentially showed is when we add lots of silica to the solution, it's actually the silica binds to the iron in preference to the phosphate. So this is the Bergman and Canfield number. This is just pure iron oxide. This is iron with something like 40 parts per million silica. And then this blue line is iron oxides formed in the presence of 130 ppm silica. When you look at these siliceous particles, you can see that the crossover is a broader range. In fact, it crosses over to modern levels. So the argument we made is that at the time that BIF were precipitating, because silica outcompeted the phosphate, phosphate would have been left in solution. There's no reason to assume that phosphate was limiting. We followed up this paper in 2010 with work by Noah, looking at the phosphate concentrations in iron formations through time, also modern iron exolites and other volcanic deposits. Now, on the face of it, if you just look at the phosphorus iron ratio, one could say, yeah, the Archean obviously had less phosphate than the modern. But if you take into account the effect of silica, so high silica, moderate silica, low silica, what you're essentially showing is that back during band ion formation, the phosphate concentrations would have been similar to today. Now, here's one thing where I'm, at that time we write this paper, this is fine. Then Carrie Ann Jones and Sean Crow and Don Canfield write a paper and say, well, what if you considered magnesium and calcium? That shows that they outcompete the silica. Where I'm going with this is back in the day, we used to argue about phosphate concentrations within an order of magnitude. As I'm going to show you, that's no longer the case. Sorry. Then we have this paper in 2017 led by Chris Reinhard, where we're looking at shales. And on the face of it, this seems to contradict what Noah and I were talking about before, because what you see is you see high phosphate content in basically in shales after basically starting with the cryogenian relative to the rest of time. And the argument is that a lot of the phosphate is being buried in what we call as a deep sea phosphate, things like vivianite, but there's also more oxidative weathering taking place later on. So it's a combination of the two. But I want to point out one obvious thing that as sedimentologists would think is dead obvious, but a lot of us geochemists seem to miss this, is we're looking at different depositional environments here, yeah? The iron formations are forming on the outer shield. The clays are forming near shore and being advected out. The shales are receiving phosphate from land, continental signature. The band iron formations are receiving phosphate from hydrothermal vents, deep sea signature. These two lithologies are tracking different things. There's no reason by looking at the BIF record that it tells us that there was much more phosphate around because it's coming from here versus this. And I think what I personally find a bit frustrating is I got lots of colleagues who do a lot of modeling, and the modeling is no doubt critical, but sometimes we shouldn't lose sight of the empirical. The BIF record is telling us what it is. The shale record is telling us what it is. The question is how do we put both those records together to come up with a consistent answer? And I think it's something like this is clearly it. And I would just point to one thing that we've known for a long time as well. Even in modern hydrothermal systems where ferrous iron comes out and instantly oxidizes and precipitates near the vent. Think of like Glohihi as a perfect example. You know, this work from Fitzsimmons from several years ago, showing that these iron plumes can actually be transported for long distances away from the source. Yes, the bulk of iron precipitates around the vent, but a lot of it gets carried far away. You know, a lot of this iron ends up forming these really colloidal particles bound with organic, which keeps them buoyant. But the point is, hydrothermal plumes can transport phosphate. And that gets me to these two papers, one from Beardre Rasmussen a few years back, where they argued basically that they found primary apatite in banded iron formation associated with green light. And they said, well, what this basically means is that at a time when lots of green light's precipitating, the iron's been driven out of solution, so there's no iron to precipitate vivianite. In other words, there's no deep sea sink for the phosphate, so phosphate concentrations could have been higher. And they went with the 100 micromole. Well, that's 50 times the modern. Then this other paper recently came out where they basically said, look, if you take a look, I mean, most of the experiments looking at vivianite were done at low pH. If you look at higher pH in the presence of a lot of iron, vivianite's reasonably soluble. You could have gotten all the way up to 4,000 parts per million. So here's where I get a bit frustrated, and it's not anything against any of these studies, but you know, 10 years ago, we were talking about an order of magnitude difference in phosphate. Now we're talking about 5 orders of magnitude. We're kind of going in the wrong direction, where some are arguing tons of phosphate, others are arguing no phosphate. What is it? And well, anyways, that's where we're at. So 2 other studies, and I'm going to be wrapping up soon, don't worry. I just want to refer to this one study, which I kind of thought was really cool that Mike Kipp and Eva Stoikin did a few years back. And what they suggest is that, look, on the early Earth, before there's oxygen, you're limited by the amount of electron acceptors. So if there's no oxygen, there's no nitrate, there's likely no manganese oxides, there's no sulfate. So if you produce biomass, who is going to oxidize it? Well, basically, you got iron reducers and methanogens. So they suggested that a lot of the organic carbon basically could have ended up buried in the sea floor because there were no heterotrophic processes around that could have oxidized it. So even though there's less organic carbon productivity, there's more burial. A recent paper that I was lucky enough to be part of with Nagisa is kind of along the same line, but we didn't talk about terminal electron acceptors. We talked about the actual enzymes. And what an exoenzyme is basically heterotrophs produce these things called exoenzymes that they basically spit out into the open environment. And these enzymes break down complex macromolecules into simpler organic carbon that then can be brought into the cell and can be respired. Now, these exoenzymes are reasonably complex. And the argument we made was that the earliest heterotrophs likely did not have the means to produce these exoenzymes. In other words, you have primary producers producing complex macromolecules, carbon macromolecules, but you don't have the cells that can actually deal with it. The cells that were around had to live basically on things like whatever was photodegraded or like photooxidized or whatever came from cell lysis that leaked out of the cells. But it wasn't until exoenzymes evolved that you could actually burn through the organic carbon. So both of them have a similar theme. It's just that there was an inefficient way of oxidizing the carbon and thus releasing the phosphate. And last couple things, the one I mentioned earlier, too little landmass. So there's this term water world. I know there's a lot of argument about how much continental landmass there was. The argument, I think, and I don't think there's a disagreement in this, but I might be wrong, is that at a time when there was much more hydrothermal activity, that the seafloor crust was thicker, much of the continents were flooded. So there was very little emergent continental crust. This is a paper that I've always kind of liked from Gayardale that relates the emergence of crust to the sulfur myth record. What they essentially suggested that in the early Archean, when most of the continents were flooded, under that high pressure, the sulfur gases released from submarine volcanoes were primarily as hydrogen sulfide. Then, when you have much more emergent continental crust and reduction in pressure, the sulfur gases being released are things like SO2 and counterintuitively H2. What they argued is that all that S2, which is now basically liberated in the atmosphere, is subject to photooxidation, forming your MIF signature. Hence why you have this big anomalous MIF signature taking place here between 2.7 and 2.5. So it's a really elegant way of trying to say, okay, as long as everything's flooded, the volcanic gases you have aren't going to lead to the MIF. But the take-home message here is that the Archean was mostly flooded. And as we get bigger continents, we have more emergent land mass that can be colonized. And that model didn't come from nowhere. I have to give credit to Lee and to Mark because they already said in 2007 something quite similar, saying that as you get emergent continental volcanism, basically the volcanic gases become more oxidizing. As they become more oxidizing, they're less of a sink for O2. So this is something that they point out. And they also point out that what is interesting is that there's other periods of time when there's no sulfur MIF record. Does that relate to periods of time when you get continental emergence? Okay. Last two things, physiological limitations. I'm going to just fly through this. Are there lots of things that basically make life hard for cyanobacteria? One, we've argued it could be toxicity, that the high iron at that time was basically toxic to cyanobacteria. They produced too many reactive oxygen species that led to things like Fenton reactions. So until the iron concentrations go down, they're not happy. The Gehringer group, Michel's group, basically said that they don't necessarily agree with us. They thought it was more along the lines that counterintuitively, that the cells had an inability of actually bringing iron into their systems. So you have these porins that can transport bulk iron, but then you have these permeases that can either bring in ferrous or ferric into the cytoplasm. And the main permeases that exist today did not evolve until much later on. So in other words, what they're arguing is that cells basically, even though they were growing in a lot of iron, it wasn't the iron that was a problem to them. They just couldn't get enough of it. So two sides of the same coin, but both arguing it's a physiological thing. And we shouldn't forget things like UVC, basically photooxidizing the cells in solution. I'm just going to skip this and lead to the very last two slides. And this is competition. The original premise of this comes from work that Carrie Ann Jones did, this 2015 paper, where they suggested that, look, you've got phototrophs growing in deep water. This is something that comes out of Andreas Kapler's paper, 2005, I think, a geology paper, suggesting that phototrophs can grow at deep levels, like 100 meters deep, with the cyanobacteria above them. The argument is this, is that if you're growing on the shelf and you've got upwelling coming up here, the phosphate in the upwelling solutions is going to get consumed by the phototrophs first, such that there's less phosphate for the cyanobacteria that are growing up here. So these phototrophs had a competitive advantage. I stuck this slide in here, not so much because I want to really argue for or against that, but this recent paper that came out of Casey Bryce's group, which is published, is kind of cool because it shows that we have to consider the competition amongst the biosphere at all given times. So while it's fair to say that phototrophs might have beaten cyanobacteria to the phosphate, once we start getting more O2, we start getting things like nitrate. Now, there's a whole completely different metabolism here of bacteria that oxidize ferrous iron to ferric iron, that's this right here, at the expense of reducing nitrate all the way to N2. So this metabolism now exists because there's O2 in the water column to give us nitrate. The interesting story from this paper is that the NO is toxic to the phototrophs. So while the phototrophs are super happy at one point in time, cyanobacteria are now moving in, they're producing more O2, which is pushing these guys down. And at the same time, we've got this new metabolism that's basically kicking their butt. So it's just kind of an interesting concept of how the biosphere changes with time. And as I promised, the very last slide, I left this one because this is the one makes a lot of sense to me, but I'm not sure what to really do with it. What I'm getting at is this. So Patricia Sanchez-Baracaldo has been doing a lot of work looking at phylogeny, the molecular clocks of cyanobacteria. And there seems to be a lot of agreement that cyanobacteria, at least the proteins that lead to photosynthesis evolved early, but the cyanobacterium itself existed already at 3.5. And I point you to this paper from Joe Bowden, where we talk about this. And there's also all these superoxide dismutases. These are the enzymes that deal with ROS evolving early on. But the one thing I want to show you right here is cyanobacteria from the rock record, or not from the rock record, from the molecular record, suggests we already had cyanobacteria at least at 3 billion years ago, these glowy bacteria, and then these things called pseudoanabina. Then around what she has at 2.4, the GOE, we suddenly get the evolution of these things called these macrocyanobacteria and these microcyanobacteria. The macrocyanobacteria are the big mat-forming species, the ones who form the thick mats that produce lots of the O2. Now, I think Joe was on. I'm not sure if Joe was on or not on this talk. But anyways, I think they have a paper coming out that pushes this to 2.6 or whatever like that. But the take-home message from this is that cyanobacteria might have existed, but the cyanobacteria that really produced modern rates of O2 didn't. And we have to wait for these guys to evolve for basically O2 rates to jump up. So in other words, yes, cyanobacteria exists, but if it's the wrong kind of cyanobacteria, it's a non-starter. It's only when the cyanobacteria that are the go-getters that really produce a lot of the O2 evolve around 2.5 that suddenly produce lots of O2. So a lot of stuff, I've actually made myself really tired. The point I want to make is there's lots of potential options for why there's a delay. If I had to pick my favorite, I would still go with habitable space. I think as long as there was less emergent land mass, there was less room for microbes on land, as well as microbial mats, meant less nutrients being supplied. I think that seems to be the most likely, but then you couple things like this, cyanobacterial species changing, and throw in there, when does aerobic respiration take place? I think there's lots of reasons that it shouldn't bother us, that there can be a big gap of, let's say, 500 million years plus to explain the gap between when cyanobacteria evolved and when we started getting the GOE. And I just lead with the last slide. For those who don't know, we've got the Geobiology Conference coming in Banff, again, the third one in next May. So it'd be good if we could see all of you there. And with that, I think I've gone over. I will leave it at that.
Thanks, Kurt. So we are now open for questions, and so people can raise hands or type in a chat room, and I will read it. Or okay.
Can I have a nap first, Andre?
Who is Kevin? Okay.
No, I said I can have a nap first because I have tired myself out. Right.
Okay.
All right, I'm ready.
Okay, Paul has questions, and I think a couple other people after him. Paul.
Yeah, molecular traits suggest that early cyanobacteria were benthic, and benthic environments cover a relatively small area of the Earth if you're looking for wet ones. And so my question is, when do you think that cyanobacteria became planktonic?
Personally, in the
Archean. The area of oxygenic photosynthesis. And so I wonder whether the delay between before the planktonic habitat was exploited could help to account for the delay in the Great Oxidation.
So I think planktonic came already in the Archean. I don't think, as Patricia showed, that Prochlorococcus and Coccus come in Neoproterozoic. Here's why I don't think that's. I think that might explain why the modern ones branch late, but doesn't tell us whether something has gone extinct. You've got organic shale. You got block shales with 10% plus organic carbon in them. You need, what's going to be the mechanism getting the carbon into those shales? It's not going to be benthic species. So I got to think that we had plankton around. Now you can make the argument, would phototrophs give you enough biomass to do it? But a lot of these shales aren't necessarily iron rich. So ultimately, I need an explanation for how did the carbon get into those shales in the Archean? So I think, what Patricia's saying makes absolute sense. If you look at the molecular clock from today, this is what it's telling you. But if something exists and went extinct, we'll never know.
Okay. Okay, good. So Lee, next, go ahead.
Yeah, thanks. And thanks, Kurt. Boy, my head's spinning. All my favorite topics crammed into an hour plus.
Good thing I put your paper in there.
Well, I'm with you 100% on the planktonic, or early origin of planktonic. And of course, it really then gets down to the aerobic respiration, because as Stephanie Olson showed, you get a modern level of cyanobacterial productivity and an anoxic atmosphere in deep ocean, and even just restricted to high productivity areas when you balance all the electron flows. So it really comes down to whether or not there's aerobic respiration. But my point here is more about Lomagundi, and just feel like I ought to bring up Aviv Bakan's work. This harkens back to Garrels and Perry pointing out that Lomagundi causes a crisis not just for oxygen but for carbon, and they argued that while pyrite oxidation can explain a lot of the things you talk about, that siderite or iron carbonate oxidation is a much more compelling component of that to provide both carbon and carbon for the burial of organic carbon. And so he generated a model. We had a paper way back when on this, showing that it's not a tremendous amount of ferrous iron carbonate that you need to be oxidized in there that can help sustain Lomagundi. And even then there are climate consequences. So I guess, the bottom line here is that we talked a lot about the limitations here, land, phosphorus, but carbon can be, when you think about the mass balance of this, Lomagundi at face value creates a carbon crisis as well as an oxygen crisis, and something like, siderite oxidation could be a part of that solution.
Yeah, thanks. I absolutely know that paper. And, when we're talking about the kaolite shuttle, we attributed to both pyrite oxidation and siderite oxidation there. I just completely forgot about it now. So sorry about that.
That's okay. Just, just keep it in the discussion that, carbon balance also, we just never think about carbon balance. Carbon's abundant, right? We don't think about it on most timescales, but, we think about it with the snowball looking at Paul, but we also need to think about it for Lomagundi as well.
So does the end of the Lomagundi mean when you run out of Archean siderite to weather?
I think that we speculate along those lines in that paper. Yeah, it's been a long while. Paul, I've been a dean too long. I don't remember what I said 9 years ago or what Aviv said. So I'm gonna have to go back and read it.
I think that's what you do say.
Thanks.
Okay. I guess Greg goes next. Greg?
Yeah, Kurt, that was really mindful. I loved it.
Thank you.
As you know, Corinne Blank and Bakalis and several other people have argued that cyanobacteria are basically a freshwater clade right from the very beginning. And you talked about them in Socros, which is something I'm very interested in. Those would probably not be rounded unicells of planktonic form. Those would probably be like Schitonema or other desert crust cyanobacteria. And it would seem to me that the argument of phosphorus limitation is really relevant here, because phosphorus is in the soils and only to a limited extent in the ocean. And it may be because they were limited to particular environments where they could thrive to actually liberate phosphorus from apatite, which is tough to do. And they also needed other microbes to help them liberate that phosphate. So I would agree with you. I think it's the small areas of cyanobacterial soils that are limiting their effect until finally they get to spread on larger continents and become more influential.
No, I agree. Thanks.
We agree. Whoa.
Yeah.
Excellent.
That can happen. I'm agreeable.
Oh, I don't know. I tend to antagonize people more than have them agree with me. So I'm unfamiliar with this concept. Thanks, Kurt.
No worries.
Okay, we move next to Mike.
Thank you.
Yeah,
And thanks
Mike.
for your talk. I want to go back to the generation of or the evolution of oxygenic heterotrophs, and that if that happened, as your paper notes, around 3.1, and that was, as you mentioned, kind of keeping pace with the amount of oxygen production, couldn't that potentially just keep oxygen production from ever reaching some higher level than we have today? If there's some, the more oxygen is available, there's more heterotrophs, and it seemed a little bit of kind of what you were mentioning, and I wanted to ask you to elaborate.
Well, I mean, the reason we get inorganic carbon barrels because we've got to push through the aerobic zone, right? So I'm just thinking in sediments. I mean, if we got fast enough barrel rates, we're going to just plow through that and get ourselves into anaerobic respiration. And ultimately, some fraction of that gets buried. I mean, and today the advantage is too, you got things like lignins and that are going to be harder to degrade. So I don't know. I got to think about what that would mean on terms of like, so in the early oceans, the amount of terminal electron acceptors that you would have had in competition, like I said, you would have started off with ferric iron, you would have had methanogens. At some point in time, when you have aerobic respiration, presuming that there's enough free oxygen around, you should also be seeing things like nitrate reduction. Now, we don't get that really into the Archean. So what I'm getting at is, in the oceans themselves, I don't know when if aerobic respiration would have been pre-GOE, because we don't really see things like nitrate before that, right? On land, though, it's a completely different thing. I don't know if on land when that could have evolved. I mean, to me, this is, like I said, this is something I don't spend a lot of time thinking about, but it is to me the big mystery of they had to evolve. I mean, they've obviously evolved at some point. The question is when. Most people would put them later than earlier. But I don't know when people look at the molecular clocks and say, well, you've got all these enzymes that all these oxidases around. If they weren't being used for O2, then presumably the oxidases were serving some other function and they were co-opted later on for aerobic respiration. I really don't know what to make of. Bottom line, I really don't know how you put these two things together. One, evidence that the enzymes that they needed for aerobic respiration already existed at 3.1, yet the geochemical record doesn't show evidence, for example, for things such as nitrate production, a lot of sulfate production at that point in time.
Thanks so much for that.
Yeah, sorry, I just don't know the answer.
But
Okay.
you explain how complicated it is, and it's not just a simple matter of you have all these heterotrophs that would use up all that oxygen because there'd be other signals that should come from that, and maybe they're not in the right place to use up that oxygen as fast, and oxygen production gets ahead of that, of using it all up. Thanks.
That no worries.
Okay, Jim, go ahead, you're next.
Hey, Kurt. Good to see you on Zoom. And fabulous talk on my favorite topic. I was thinking about your earlier point on the acidity when you weather all the pyrites, and when you have higher acidity, the solubility of organic carbon decreases. Right? So the mobilization of organic carbon on the string on suspension is going to decrease. But also to kind of enforce this mechanism of organic carbon retention in situ, is that in the modern atmosphere, right, we have the productivity of oxygen like 4 orders of magnitude higher than the organic carbon barrier because the respiration, and that in the Archean may not be a case. At least there shall be a transitory effect on that. So both of the thing I discussed pointing out there shall be a better retention of organic carbon in the Archean. But are we seeing that in the paleosol? Oh,
Well, what I do know about the paleosols, and Andre can probably jump in about this, but I mean, there is like evidence of, I mean, Hiroshi Emoto talked about this, but the 2.8, there's the Mount Road, it's got evidence for O2, I think. But I think there's, I mean, one of the points Hiroshi made is that there is organic carbon in these Archean paleosols. I don't know, Andre, I think Mike Babchuk was online as well. You guys work more on paleosols, but there is organic carbon, like the Schengen one does, right?
Well, that's I'll chip in here. That's one of the things that Dick Hall and I talked about a lot. And the amazing thing is that all the Archean paleosols have organic carbon in the right isotopic ratios and all that, but it's very low. It's about the same as you'd get in a Phanerozoic paleosol. So they're not accumulating more organic carbon necessarily, except in small environments, but well-drained ones, which Dick concentrated on, have rather low organic carbon, which suggests there's some sort of decomposer cycle in the soil as well. And I think it was Cyanobacteria, which I found at 3.0, and in other paleosols too, 3.2.
I think there was a paper recently by Axel Hoffman on South African paleosols with organic rich. I didn't read it, but I think it was in Precambrian research. Okay, Paul, you wanted to say something?
Well, carbonate delta C13 is 0 per mil, more or less, in the Archean, so it doesn't look like there's been a, you know, a big change in fractional organic burial. And I've forgotten the question I was going to ask, but I'll take my hand down and see if I can remember it.
Was it to have anything to do with the fact of saying that early on more organic carbon got preserved because you didn't have the electron acceptors?
So I say it again?
Is it because, you know, I was making a point that if you didn't have electron acceptors or you didn't have the exoenzymes that break down the carbon, you would have presumably buried more of the organic carbon?
Yeah, well, what I'm saying is that the carbonate carbon isotope suggests that fractional organic burial has not changed between the Archean and post-Archean, you know, on average. And it's hard to change the carbonate burial because that's just you know, rock weathering. Incidentally, this wasn't what I was going to ask, but I'm very skeptical about this business about no Archean land areas. I mean, if you look at Archean rocks, there's lots of evidence of terrestrial erosion and non-marine clastic sedimentation, like the Moody's, for example.
I didn't mean none. I meant just limited.
And you can say, well, those are just small areas, but it's true today that the areas where continents are being eroded are relatively a very small percentage of the total area of continental crust. So it's the areas at plate boundaries where the crust is being thickened. That's where the erosion occurs. And there's every evidence that that was true in the Archean. And, you know, and in addition to that, freeboard, I would say, is controlled by sea level itself through the dual processes of sediment accumulation and erosion. It's not, so freeboard is not an independent variable.
All right, so, okay, so the take-home
message.
message.
The question I was going to ask was, it took streptophytes 500 million years to terrestrialize, which is not an easy trick. So why do we think that cyanobacteria were able, you know, to invade the land so easily and early?
But where do you suggest they started?
In coasts, in coastal areas and wetlands, you know, where mats occur today.
Okay, but I mean, I don't know how I would agree with you or disagree with you, because I mean, one way or another, we've got them starting somewhere. I mean,
right, but those are relatively small areas.
Yeah, no, I agree with that.
Coastal zones.
that's to the point is that, you know, when the argument, the reason I'm making with the landmass, the reason I'm making that argument is that when you take a look at the people who do the modeling and saying how fast can you burn through all the reductants, if you look at modern O2 production rates, you should be able to do it pretty fast, but we're not. So we're stuck with why is that the case? And it just seems to me like that, like, again, it's like, where are these guys growing? I mean, prior to having decent continental shelves and stuff like that, would they be able to on a fringing islands, would they have as much space to colonize as they would with a decent sized shelf with these carbonate platforms?
Yeah, well, I'm just saying that you know, living in areas that are episodically dry and subject to desiccation is very difficult for organisms to do to be able to adapt to those kind of hostile environments. And
But there is work that's been done on
fact
molecular clock
that
and
streptophytes evolved 800 or 900 million years ago, but you know, it wasn't until the Siluro-Devonian that terrestrialization really took place in a big way. Is an indication of how difficult that transition is. I think Greg can speak more knowledgeably about this than I.
Yeah, I'm actually on Kurt's side on this. I think life on land goes way back, well, even before the beginning. But that's another. I wanted to introduce another wrinkle here. My studies of Archean soils have shown an amazing amount of sulfate in them, as desert roses, as sand crystals that were precipitated in land. And the Farrell quartzite biota, for example, has these purple sulfur bacteria from isotopic composition and morphology, and methanogens, and actinobacteria as a community. So one way to delay the rise of cyanobacteria is competition between purple sulfur bacteria and cyanobacteria, which is something that it's easily studied even in modern environments, in lakes and in desert crusts. So I'm just throwing that out as another way to deal with this delay. What do you think, Kurt?
Well, you know, I have no problem with. I just gave the argument that they could do it in the marine setting, that they could outcompete. Be honest with you, I don't know much about the proteobacteria on land, so.
Oh, they're in playa lakes. They're in desert soils as well. And they're largely responsible for these things called desert roses, these gypsum crystals that have a lot of included sand grains in them. And I see Christoph's signing on. He has them in the Moody's as well. They're quite remarkable.
Sunlight.
Okay, so I think Eva had
Christoph, his hand up.
Well, I took my hand down because Greg just stated what I meant to say. And Kurt, you and many others have looked at the Moody sulfate concretions. And these are paleosoils of 3.2 billion years age. Greg is right, there's a very low TOC in them, but they are interbedded with these benthic bacterial mats, of which we do not really know whether they are cyanobacterial or not. But we do have the base drill cores, which are currently being worked on by Eva Stüken and Stefan Lalonde and Takeshi and many other people. So word should be out within a few years.
No, I do recall them. Yes.
Okay, yeah, thanks for your talk. So you mentioned the recent work by Patricia Sanchez-Baracaldo on these cyanobacteria. And so I wonder, so if she's correct in saying that these thick mat-forming cyanobacteria only evolved around 2.6 or so billion years ago, so can you think of some kind of environmental parameter that could have maybe, I don't know, if it triggered that evolution? So are there certain environmental conditions that favor these thick mats somehow? And could that tell us something about paleo environments?
No, I've talked to her about this before. No reason I can think of why they would suddenly think 2.5, 2.6 was the right time to evolve into, whether it's just a developmental thing.
Okay. All right, thanks.
Okay. Greg, do you have something to add, or you just?
Oh, I'm done. Sorry, I should have taken it down. Thank you. Excellent. Thank you.
Okay, Kurt, I have a couple questions. Maybe I ask separately. So, so you started with sort of aerial end bar metal enrichment in black shales, and when you went to microbial mats on the continents that produce oxygen and oxidize and release metals. So I'm just wondering how you imagine transport of these metals through rivers in anoxic environments to get out on shelf and into more deeper environments to be still soluble and be enriched in black shales, sort of like in what form they would be chelated, or in what form they would be still soluble to make our way to deeper water environment to get into this black shales.
I think the answer to that's probably clays. We've shown this now with phosphate. We've shown the same thing with chromium. I'll just go as an aside for others. So one of the criticisms I had on my chromium paper was saying, okay, you have a pH of 4 or 5, whatever like that, and it's carrying the chromium. And people have rightly said, well, going through a catchment, how long is that pH going to stay at that level before it gets buffered? And what we've done is we've done experiments with things like kaolinite, where the chromium binds to kaolinite, does the exact same thing. At pH change, chromium just desorbs. I can't help but think that with a lot of these trace metals, it is being sorbed onto things like clays and mobilized that way.
And just continuing on this question, like if it's indeed clays, then why, what is so special in Mount McRae? Why it has this high concentrations? Like you would have clay production and cyanobacterial mats at 2.6, 2.7. Why? What made this shale so special?
Well, I guess the flip side, why is it so special if it was transported by mats versus why is it so special that time that there was O2 for millions of years?
Special in terms of high concentration compared to other shales.
Well,
like what?
I mean, in terms of the concentration, I mean, the molybdenum, it's like we're talking like tens of ppm higher, I think, for a period of time. I don't know. I mean, are we? I mean, I don't want to start questioning all the WIF stuff, but I mean, are we 100% sure that all the metals in that are necessarily land-based?
Yeah, that's another argument.
I mean, because, you know, Bill Seaford has been showing stuff like that, things such as molybdenum there can be more molybdenum coming from hydrothermal systems than we thought.
Yeah, but when again something hydrothermally happened unusual at that time to make it unique compared to other shales. I think we have maybe. Yeah.
There's arguments for and against, right? I mean, the thing is, the Mount McRae shale has the equivalent stuff in decline in South Africa too, right? Where a lot of the work that Brian Kendall and them have been working on, and same with Ariel, that's seeing the exact same thing. So rocks at that time seem to have this enrichment. But is this, you know, the thing with the oxygen oases, my problem with I don't know if problem is the right word. I'm trying to imagine, I can envision having oxygen at that time in a higher transition state throughout the atmosphere, oxidizing everything at that time. But the whole thought of oxygen oases being sporadically interdispersed, oxidizing certain areas, I just don't know how that works.
Yeah, that's okay. I just wanted.
Yeah.
And second question, sort of, you draw this picture with very little phosphorus coming from continents on a shelf and low concentration of phosphorus in the shales. And when phosphorus coming from hydrothermal systems and ion formations being rich in phosphorus. So I just wanted to ask you more about it. Sort of in modern world, hydrothermal system are sinks of phosphorus, and you implying that it was a source of phosphorus. And
Well,
I can
it's
get
a sink today because you've got iron oxides, which you didn't have then.
Yeah, I can get it, but in an oxic ocean it would spread further. But basically, you need to deliver a huge amount of phosphorus from hydrothermal vents to do it. And
Well,
then basically you bring in it in the same depositional site. You have shales overlined by black shales, shales overlined by iron formations, and you have low concentration in shales and maybe sea level increased to deposit iron formation, but still it's the same depositional site. And when iron formation at this site show high concentration. So I don't know if you have any thoughts like on more details, how you envision it.
But remember what I'm saying about the iron formations is that they're not a massive sink for phosphate because of the silica.
Okay.
Right? If there would have been a deep water Vivinite trap or something like that, or if the whatever with the green light, I mean that rock record part's gone. I have no idea. But I might just add, I'm just saying what Bearder and Nick Tosk and them have been arguing recently. It's not necessarily saying that I necessarily agree with it.
Mm-hmm.
The point I was making with the caution is just saying that you're looking at two different lithologies that are from in different locations. They should tell us different things. Yeah. And I'm not so quick to take a look at that 2010 paper from NOAA and say, I don't believe it anymore because the concentrations we have in there are real. Question is the interpretation for it. So it's a matter of taking Chris's shale record with NOAA's BIF record and saying, well, what's the common denominator between the two, if there is one?
Yeah. I mean, even for silica was high, and maybe less phosphorus was taken down with iron formations. On the other hand, iron formations volumetrically large, so even with small intake, they can keep phosphorus low, I guess. Because otherwise you have problem like where did phosphorus go? It's not in shales and it's not in iron formations.
I mean, where Bearder and I agree is with things like you could precipitate green light in the deep sea. There's no reason why you wouldn't, but we'll never know. That record's gone. Right, so we're just using what we've got preserved on the shelf to tell us about the bulk ocean, but I don't know if we can do that.
Yeah. Okay, good. Any other question? Paul had a hand up, but it went down now. Do you have
I was just going to add regarding your comment about the Mount McRae shale, is that 2.7 is a very prominent peak in zircon age frequency.
Sorry, well, can you explain to me what
it suggests that it could have been a period of unusually high rates of terrestrial erosion.
Oh, okay.
Weathering.
Yeah, the interesting thing about Mount McRae, it's not in only one drill core that we see this enrichment. It's actually even Hiroshi Amota and his group in a different drill core saw enrichment and also geological survey Western Australia. So it seems to be this enrichment spread at least in 3 drill cores through Hemisphere province. And whatever source of it, hydrothermal or weathering on the continent, or some people argued that it's later hydrothermal activity, but it has to be widespread on the scale of whole basin.
What's the status of the cracks and tertiary weathering idea?
Well, I think it was published by Caltech group, and I think people wrote comment on it. So I think it's still quite open. I mean, you would think that again, it's not unique process. It's not like Mount McRae uniquely affected by hydrothermal activity. But yes, there is enrichment in cracks, but some of it it came from the same rocks, so it's kind of. But I don't know. I didn't look closely into it. Okay. Any last minute question? Kurt, you kept people for almost hour 40 minutes and still at least 20 people in the room.
I'm so ready for a beer, I have to be honest. It's like 5:45 Manchester time now, so.
I'm ready for the next issue of geobiology.
Hey, make sure, Paul, you come to the meeting in May this time.
I'm enjoying Grettenberger and Don Sumner. It's nice to see Don Sumner back in deep time.
Yeah, no, he had that AEM paper that I thought was quite interesting about the Lomagundi. So
yeah. Okay, thanks,
Okay.
Kurt.
well, thanks everyone for sticking around.
Thanks, Kurt, again, and we will have a next talk next week. Okay, talk to you all soon.
Thanks all.
Bye.